Hey guys, welcome to chemistry. A little bit different setting, a little bit different situation, kind of strange, out of the ordinary, but maybe it's kind of fun. Something different, right? So, we'll make the best of it. We'll get through this. We'll go a little bit slower than we normally do, but that's not bad. Maybe this will work out. It'll be a recorded lesson and you guys can watch it again if you have some trouble with it. You'll still be able to get in contact with me and get as much help as you need. So, hopefully this all works out. So we've been talking about thermodynamics and delta H and heat is what we spent most of our time with. We've been talking about endothermic and exothermic reactions. We're going to continue to talk about that. And one of the things that we did the previous week is we did some examples on endo and exothermic reactions. And you remember one of them, I mixed two chemicals together and they were in a beaker and they got really, 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 really cold and they basically froze. And they froze that wooden block to the bottom of the beaker. And it dropped to negative 20 degrees or something like that. And we've learned that endothermic reactions usually don't work very well. So let's take a quick look at that endothermic reaction really quick. So I was able to find a guy on YouTube doing the same thing. And so you'll notice in this picture we've got the white crystals. And the white crystals are mixed together and he starts stirring. So let's take a quick look at that. So we got...
crystallizing dish, which is held firmly over the wet filter paper. A slurry is formed as the hydrated barium hydroxide and ammonium thiocyanate solids react to produce products, including water,
Alright, so I'm going
which
to
they
grab a
dissolve.
capture of that right there, and we're going to switch right over here to this picture. Now, when we look at this picture, remember we said that it's an endothermic reaction. So if we think about this in terms of a mountain, the boulder is rolling up the hill. This is not a favorable reaction according to nature. You've never seen water running uphill. You've never seen a boulder rolling uphill unless somebody is pushing it the entire way. So maybe this reaction requires energy and needs help. And so maybe this guy is trying to give it a little bit of help. He's obviously stirring it. But is stirring enough input of heat? And so when we talk about energy, it's heat and light. And so it's pulling heat in. How is the stirring providing us with all that energy? It's not. So when we're doing this, there must be something else that's allowing this reaction to go. It's not like he put it on a stove, he doesn't have lights on it. Something else must be forcing it. And you'll notice, remember we said that in the beginning it was a solid. And now when we look at it, it's wet, right? That's definitely not those white crystals that we started with. It's a liquid. And not only is it a liquid, but it's also making a lot of gas. You can't see the gas here, but when I did the reaction in class, I could definitely smell it. It was really powerful smelling. It's like a cleaner, like ammonia's and all kinds of different cleaners. It's very strong smelling. This phase change that we're seeing here, solids turning into gases and liquids, is a very favorable thing, this phase change. This is a new variable that we're going to look at, and this is called delta S. And we like to see delta S's getting messy. And so let's pop over to notability real quick. We want to see this sort of messiness that I'm talking about. This messiness, this delta S has a name. And so when we're looking at this slide, so you guys have copies of this on Classroom already. We started with a solid. A solid, really by definition, is the most organized form of matter, the most organized state. Crystals. So you go from that solid to a liquid and you get messier. You go from that solid to a gas and you get really messy, right? A gas is sort of like the most messy of all the phases. So this was a reaction getting really messy, and nature loves that. Anybody who's ever owned a pair of earbuds knows exactly what I'm talking about. You carefully wind that up so it's very organized and nice in your hand, and then you stuff them in your pocket. When you pull them out, I don't care how careful you were, they're a tangled mess. Right? That's just the way it is. Think about your room. Think about your binder. It takes work in order to organize things. They just seem to naturally want to fall apart and get messy. And so when we see reactions doing that, we're usually pretty happy about it, and so is nature. So if we glance at a reaction real quick, let's just take a look at an example here. Maybe we've got this one. We started with some gas here, and we started with some gas here. not only do we have some gas, we actually have 2 moles of gas. So on this side, we have 3 moles of gas. We look at the product side, we still have some gas, but there's only 1 mole. What did the rest of it turn into? It turned into a liquid. So in this particular reaction, I would make a guess and say that it's probably not a favorable reaction. I see gases turning into liquids, which means they're basically getting organized all by themselves. And that just doesn't sound right. But we could double check this. It's tough to just go off of estimation. It's okay to estimate, and I might ask you to estimate on a test or something like that. But there's a way to check it for sure. And so what we do is we flip back over here to our old friend. So before, we were using delta H, and we had a column for that. Well, we also now have a column, oops, didn't mean to erase that, a column for S. And so when we were looking at that equation, one of those chemicals was that CH4. And so we see that CH4 has an actual value right there. It's 186. So I'm going to go ahead and put that down, 186. Now oxygen, we normally wouldn't look up for a delta H value, right? It's a pure element. Nobody had to form it. That boulder didn't go up or downhill. But with S, it's a little different. Some elements are just naturally messier than others. Some on the periodic table are solids, some are liquids, and in the case of oxygen, it's a gas. We know the gases are pretty messy. So when we look back at that table, we'll have values for S, and you see it right there. Oxygen's a 205. So it's 0 for the other one, but 205 for our S. So we're going to go ahead and plug that in. And to save us a little bit of time, I already looked up the others. We have 214 and 70. So what do we do with these? Exact same thing we did with delta H. It's super easy. So we're going to go ahead and go delta S is equal to products minus reactants. And so we plug that in, and we get 214 plus 2, because we can't forget this coefficient right there, times 70, minus my reactants, which is 186, plus, once again, don't forget the 2, times 205. And when we plug that into our calculator, we get negative 242. Now, when we go to put our units down for this, a lot of people are used to putting kilojoules per mole, but S is a little bit different. We see that it's joules per gram. So we're going to come back up here and put joules, oops, not per gram, per mole Kelvin is what I meant to say. And so when we look at this, our prediction was that it's getting more organized. Liquids are more organized than gases are. Is that what our value here tells us? Well, let's take a look. We have a negative number. So that means that something is decreasing. That something is entropy. And what was another word for entropy? Messy. The messy is decreasing. It's getting more organized. Our number matches perfectly. So sometimes we get some that are really hard to estimate. This one wasn't too bad, but sometimes they're hard. And we have these numbers that'll tell us true. Now, if you look at this reaction, it shouldn't be a surprise that it's not favorable. It's probably not going to work, because this has got oxygen, carbon dioxide, and water. This is a combustion reaction. And have you ever seen a combustion reaction make liquid water? No. It should have been a gas. And so if we go back through and we were to redo this math using water as a gas, odds are it would probably be a positive delta S. The messiness would be increasing. And so that would be what we expect. So with that in mind, that's really all we're going to do today. You're going to have an assignment. You're going to look some values up, and you're going to subtract them. Products minus reactants. You're going to tell me, is the entropy increasing or decreasing? Is it getting messy or organized? That's what I want to see. Messy or organized. So in this situation, my answer would have been organized. Now, if you're having trouble with any of this stuff, I want to make sure that you guys ask me questions. Get online, send me an email, hit me up on Classroom. Any of that would be great. If necessary, we can always get a Zoom meeting going, and I'll probably get the homework out and solve a few of them myself and record me solving these and let you guys see those answers the following day. So you'll want to get that homework turned in, take a picture of it so I can see that you did it, and then once everybody's got their homework turned in, I'll put the answers up and show you me solving a few of them. And hopefully that'll take care of any last minute questions anybody's got. Okay, it's been great helping you guys out. I'll be in touch.